All right, so before we get into the three types of radioactive decay, let's just kind of go over the background of why some atoms are radioactive and undergo decay and why others don't. And if you think about the title of this whole unit, it's nuclear science, so it's going to deal with the nucleus. So the reason that some atoms undergo radioactive decay is because the nucleus isn't ideal. The particles in the nucleus are neutrons and protons. And if there's the correct ratio between the two, then the nucleus is boring and stable. In the video, we saw that that was like a brick in the fire. However, if the ratio is not quite right, then it looks, or in the video at least, it was represented as a dragon. It was ready to spit out fire or spit out particles or spit out energy, or it was going to change or morph into either a brick or a different dragon, maybe one that wasn't so unstable. When we dealt with the PhET simulation, the little nucleus was shaking and shaking and shaking, and that was representing our unstable atom. And then when it was stable, it just stayed put. It was boring. So unstable is an atom that is ready to decay. At some point, it's going to change, and it's going to become more stable. Sometimes it becomes like a brick, completely stable. Boring, doesn't change. Other times, it just becomes more stable, but it might be a different element that's still unstable, but at least it's better than it was with the original parent. So we have this parent that's always unstable. It wants to change because the nucleus, the ratio between neutrons and protons, isn't quite right, and it will become a daughter. And it's going to spit out fire, which is the radiation we're going to talk about in a second. Now, real quick, just make sure that you understand mass and atomic number. Remember, mass number is protons plus the neutrons. That's your mass number. And on the bottom is your atomic number. This is just protons. So if you're given this information, you could subtract and find out how many neutrons there are. And then you can look at the protons and the neutrons and look at the ratio between the two. If it's a low element, meaning it's not very heavy, one of these little guys, the orange band here is right on this black line that represents a 1-to-1 ratio. So if you have 6 protons, you have 6 neutrons. If you have 10 protons, you have 10 neutrons. That's 1-to-1. That's going to be right on this line. That's going to be on the band of stability. That's boring, stable. But if you find yourself up here or down here, you're not on the band of stability. These are our dragons. These are the ones that don't have the right ratio, so they need to change to become more stable. Okay, so there's 3 types of radioactive decay that we're going to be focusing on: alpha, beta, and gamma. So we always start with our unstable parent, and SY stands for symbol, whatever element this is. The mass and the atomic number are on the left here, and the ratio of protons and neutrons are not the right ratio. So this is unstable. Over time, at some point, this atom, this unstable atom, is going to undergo decay. It's going to change. Just think decay, change. It is going to become a new daughter atom that is more stable. Sometimes it might be perfectly stable like a brick. Sometimes it just might be more stable, this little nicer dragon. Sometimes it might have a new identity if the atomic number changes. But that's always going to happen. We're always going to end up with something in this spot of our chemical or our nuclear equation, and we always have something over here. This is what comes out of the atom. Now, it can be an alpha particle, which is written with this little letter, like Greek letter A here. Here is an alpha particle. There's 2 protons, and there's 2 of these gray neutrons. That adds up to 1, 2, 3, 4. That's why we have a 4 up here, and the fact that there's 2 red ones, that's why we have a 2 down there. And if you look on the periodic table, what element is element number 2? Helium. So this is our alpha particle. A beta particle is an electron that does not belong in the nucleus. So this little beta particle, this little electron, comes flying out of the nucleus. And remember we talked about electrons really having such a small mass that it doesn't even count. when we figure out the mass of an atom, we always count just what's in the nucleus, protons and neutrons. That's what contributes up here to the 4. It's the protons and the neutrons. Electrons don't really count. It's like dust on your shoulder when you stand on a scale. It's not going to make a difference. So that's why there's a 0 in the mass spot. And down here, if it was a positive 1, we would indicate that it's atomic number 1. It's an element that has 1 proton, which would be hydrogen. But this is not hydrogen. This is not a proton. It's actually the opposite charge of a proton. That's why it's a negative. So this is how we represent a beta particle. And finally, gamma energy is very energetic, very high frequency, high penetrating power, can do a lot of damage. This is very dangerous, and it's all energy. There's no mass, there's no charge, and it's represented with this funny looking kind of a Y symbol here. This is a Greek letter gamma. So when we are told that something is undergoing alpha decay, then we're going to follow the same process every single time. We're going to take this top mass number. Remember, this is the mass here. This is protons plus neutrons. And we're going to subtract 4, always. Math is not hard. Subtract 4. And you're going to end up with your new mass number here. It's going to be 4 less. Then, where did the 4 go? Over here. The bottom number, you're always going to subtract 2. Why? Because 2 of the 4 that come out are protons. It loses 2 protons. So this number, the atomic number, is going to go down by 2. So it's going to be 2 less. This is going to be a different element. Because it's a different atomic number, it's 2 less, you're going to have to look on the periodic table and look 2 lower. Go down 2 and find what the new element is, what the new identity is. And then where do those 2 protons that came out go? Right over here. So we have 4 over 2. If you look on the periodic table, what's got an atomic number of 2? Helium. Or you could write the Greek symbol for alpha. Now, let's do a real example here. We've got bismuth undergoing alpha decay. I'm telling you it's undergoing alpha decay. I could have written this. That would have been a symbol or a signal that it's undergoing alpha decay. But otherwise, if it was just all blank here, you wouldn't necessarily know what it's doing. So now that you know it's alpha, you're going to run the same mathematical process that we talked about up here. Subtract 4. 214 goes down to 210. The bottom, always subtract 2. It always loses 2 protons. 83 now becomes 81. So our new, more stable atom has 81 protons. So look on the periodic table. What element has 81? It's not bismuth. It's thallium. TL, thallium. So we have a new element here. And then, where did everything end up? In that little alpha particle that comes flying out. There's 4 total particles, subatomic particles that come out. 2 of them are protons. And we can represent it with the little alpha symbol or He. Beta is mathematically pretty simple, but the reason why it's changing the way it is a little bit more complex. What's going to happen is the top number, the mass number, is not going to change. It's going to stay the same. So whatever you write here or whatever you see here, you put the same thing here. They match. And if there's no change, we're going to put a 0 here, which makes sense. 0 plus whatever this is still going to equal this. The bottom does change. We're going to add 1. So whatever you have for an atomic number, it's going to go up, add by 1. So you have to look at this number, add 1, come up with this number, and then because this is a new atomic number, you're going to end up with a new element. So you have to look on the periodic table, but instead of going down 2 like we did with alpha, you're going to go up 1 and find out the new identity or the new element. And then put that here in the symbol spot. Now, how do we represent the increase of 1? Well, we're going to put a -1 here. That represents the opposite charge of a proton. This represents the little electron that comes flying out. That's our beta particle. It's an electron which has the opposite charge of a proton. Now, why does this happen? The top number stays the same, even though some changes take place, because the changes cancel each other out. Up here it says it loses a neutron but gains a proton. So let's talk quickly about this particular nucleus. Inside the nucleus, we have 29 protons and we have 37 neutrons. The neutrons and the protons, not a one-to-one ratio. So the neutrons say, you know what? I've got an idea. One of us is going to sacrifice ourselves. One of us is going to stop being a neutron. We're going to reduce the number of neutrons by 1. So 37 is not going to be 37 anymore. It's going to go down by 1. It's going to be 36. Now, what happened to that neutron? Well, it became a proton. Protons are going to go up. 30 is going to be our new atomic number. Now, we started with 29 and 37. That was 66 total. And we end with 30 and 36. Again, we got 66 total. That's why we never change our top number. Don't change the mass. Just rewrite it. The bottom number does change. We started with 29, ended up with 30. 29, now we have 30. 30 is not 29. So this element is going to be different than this element. So you go up on the periodic table by 1. What comes after copper? Zinc. So this is zinc. So now we have an atom of zinc. And then what else is formed when this change takes place? When a neutron becomes a proton, it also produces a little itty bitty tiny electron that has no mass for our purposes, the opposite charge of a proton. This itty bitty tiny electron looks at the rest of the stuff in the nucleus and says, I don't belong here. I'm getting out. And it comes flying out. All right, in gamma decay. Now, radiation can take the form of either particles, which we just saw, alpha and beta, both particles, or energy. Gamma is the energy. It's very, very intense energy. It can do a lot of damage. It is something that you want to avoid at all costs. This could be lethal. The math for this is unbelievably simple because no particles come out. It's just energy. And the analogy I like to use, and you probably saw it in the notes, is you've got this crazy hyper dog. It's running all over the place. It's super excited to see you. You run outside with this dog. We're going to consider this dog to be unstable. It's got lots and lots of energy. So you run around with this dog. You come back inside, and now the dog is nice and calm. It is stable. It's not doing anything interesting anymore. But when the dog was outside running around, burning off the energy, it wasn't losing body parts. It wasn't changing and becoming a cat. It wasn't doing anything interesting other than burning off energy. So you don't change the mass number because protons and neutrons don't change. You don't change the atomic number because the protons don't change. And you don't change the element's identity because the protons don't change. And you don't put anything in these boxes other than zeros because the protons and neutrons don't change. The only thing that does happen is that energy comes out. So we use this funny looking Greek symbol Y, that wasn't a very good one, to represent the gamma energy. So if we were dealing with an equation here, we just copy. If we start with 60, we end with 60. If there's 27 protons, we still have 27 protons. If it's cobalt to begin with, it's still, oops, that should be a lowercase o. It should still be cobalt. Do a better job. CO. Otherwise, it would look like carbon monoxide. We don't want that. So everything stays the same. That's what I mean. Gamma decay is the easiest one to do. And then over here, 0, 0. Remind yourself there's no particles there. It's just energy.